This lecture begins damped harmonic motion. This lecture is specific to physics AB. There is no such thing as a simple harmonic oscillator. Instead, there are only damped harmonic oscillators. The reason for that is because as a spring, for example, is alternatively stretching and compressing, due to molecular interactions that occur within the spring, energy is being lost as heat. In other words, there is no such thing as an idealized spring. Now, mathematically, it turns out, describing the force that causes all of this, what is called the damping force, is actually quite easy to do, even though the actual physics of what's happening here inside of this compressing and stretching spring is in fact quite complicated. So even though it does seem complicated, as we'll see in just a few moments, describing damped harmonic motion and the damping force that causes it is actually pretty simple and rather straightforward. So once again, there is no such thing as an SHO, there is only a DHO. Ultimately, there is no such thing as an idealized spring. Energy is lost as heat in the compressing and stretching spring, and this is completely unavoidable. Okay, let me go ahead and retilt my phone. There we go. Let me tilt it upwards as well. So bear with me, please. Thank you. Okay, so let's now go ahead and take a look at the DHO. This stands for a damped harmonic oscillator. Okay, ultimately, there is no such thing as an idealized spring. Energy is lost as heat in the stretching, compressing spring. Okay, the damping force is a description interaction of matter within the spring that causes the heat loss. Okay, now how does the damping force mathematically behave? Well, first of all, like the spring force, the damping force is a restoring force. What the damping force is ultimately trying to do is it's trying to bring the oscillator back to the equilibrium position with no energy. So then therefore it would just simply end up at rest at the equilibrium position. In addition to that, it depends directly upon the speed of the oscillator. Basically, the faster the oscillator is moving, this then means the greater the rate at which energy is being lost as heat as the spring is stretching and compressing. So then therefore, because of that, even though mathematically it's difficult to describe all of this in terms of the physics, empirically, however, it's actually rather simple and straightforward. The damping force is directly proportional to the speed of the oscillator V. Now, when quantities are proportional to each other, this then means that there is another coefficient here that turns all of this into an equal sign. That coefficient is referred to as the letter B, and it's called the damping coefficient. Okay, the damping coefficient is an empirical property of the spring itself. It's basically a function of what the spring is made of, how thick the coils are, and so forth and so forth. It's basically a measurement of how quickly the energy is being lost as heat. So the basic idea is actually rather simple and straightforward. That is, the faster that the oscillator is moving, the greater the rate at which energy is being lost as heat, therefore the greater the damping force. Now, when you take the damping force into account, along with the spring force, that is, F equals ma, becomes a much more complicated differential equation. Even though, of course, in this algebra-based course, we are not going through all of the necessary calculus. However, let me go ahead and describe to you what F equals ma looks like for such a situation. Okay, so let me do some erasing. Okay, so when we take the damping force into account, then we have the following two forces then giving us mass times acceleration. So we have the spring force and now we have the damping force. This is a pretty complicated differential equation because, for example, as the position is continuously changing and the velocity is continuously changing, therefore the acceleration is continuously changing. Visualizing the solution to this differential equation, however, is actually pretty simple and straightforward. The easiest way to visualize the solution is actually to graph out the solution. So what is the solution x of t? Well, what I'm going to do is graph out the solution as a function of time. So what does this solution look like? It's actually rather simple and straightforward in terms of describing it. It helps, however, if we take a look at the oscillation once again. So let me retilt my phone. Like so. Let me tilt it downwards as well. There we go, like so. Okay, now let me set this into oscillation like so. Okay, what you're seeing here for the solution to the differential equation for the DHO is actually the product of two functions. One of those functions, first of all, is just a cosine curve because after all, we're talking about an acceleration. And then the second function is describing how the amplitude is decreasing with respect to time. If you watch this oscillator over the course of a couple of minutes, you'll begin to noticeably see that the amplitude is decreasing with respect to time. So what I'm going to write down first of all is the graph of this function, which is very easy to visualize, and then we'll actually take a look at what the function itself looks like. So let me retilt my phone. And let me tilt it upwards as well, so bear with me, please. Okay, there we go. Okay, so first of all, the graph. So the graph that you're seeing basically looks something like this. Like so. Where what we have here, first of all, is an oscillation. So there's going to be a cosine curve present. But also take a look at the amplitude. Notice that the amplitude is undergoing a decay. That is like so, as time goes on. In fact, it's actually an exponentially decaying amplitude. So we have an exponentially decaying amplitude as time goes on, combined with a cosine curve. So then therefore, ultimately, the solution to this rather complicated differential equation looks like this. Okay, let me write down the function here fully, and then I'll explain it. Like so. Okay, first of all, take a look at the function. Within the function, you're basically seeing two things. First of all, of course, is a cosine curve, because after all, we're talking about an oscillation. But then right here is what is referred to as the amplitude term. The amplitude term is describing an exponentially decaying amplitude in terms of the base of the natural logarithm, the number e, 2.71, and so on and so forth that you've seen from math class. So this right here is sometimes referred to as A of t, and it's called the amplitude term. So we have an exponentially decaying amplitude being multiplied by a cosine that describes the function above. Now, notice the angular frequency omega. The angular frequency omega is different than that of the angular frequency of the SHO. Recall that the angular frequency of the SHO was equal to the square root of k over m. When you take damping into account, you end up with this extra term here. Okay, because these two quantities are distinct from one another, we now sometimes refer to the SHO's angular frequency as omega naught, and we also give it a name. We refer to it as the spring's natural frequency. Okay, now as I described in a previous lecture, ultimately this expression here comes from solving the differential equation of the SHO. We saw, however, how that expression has to work the way it does algebraically by using conservation of energy for this algebra-based course. Okay, where does this expression come from? Well, for those of you that do have a little bit of experience in calculus under your belts, let me give you an idea as to where it comes from. What we do is we take this very complicated looking position function and we plug it into here. And then we have to take its first derivative, which involves multiple chain rule, for example, and product rule. We take the first derivative and we plug it into here. And then the situation gets even worse because then we have to take the derivative of that, the second derivative of position with respect to time, and plug it in for the acceleration here. When you do all of that, which requires the better part of 45 minutes, for example, if I was going to explain it on the board, you then ultimately end up with this expression here coming out of the mathematics. The angular frequency is not quite the same thing as that of the SHO when you do, in fact, take damping into account. So there's really no way around the calculus to show mathematically where all of this comes from, but the easiest way to visualize where it does come from is by looking at the graph here of the position as a function of time. Okay, last thing about the mathematics associated with the DHO before we take a look at a simple example problem or two is the description of its energy. Okay, let's make a comparison between the SHO's total energy and now the DHO. Recall that the SHO's total energy E is the following expression, 1/2 Ka squared. Now I didn't graph this out at the time, but it's useful to do so here to compare it now to the DHO in just a moment. Okay, so for the SHO, if you graph out the energy as a function of time, because it is constant, you just end up with a horizontal line like so, and a value of 1/2 Ka squared. What happens now when you take damping into account? Well, ultimately the energy is once again a 1/2 Ka squared calculation. It's just that now the A, the amplitude, is this quantity right here. So then therefore for the DHO, the total energy as a function of time is 1/2 Ka squared, but now we take this quantity here and square it. That then ends up giving us the following. Notice a slightly different exponent here as opposed to here. When you take this quantity here and square it, basically you take the 1/2 that is here and multiply it by 2, ending up with this right here as your exponent. Once again, to show all of that involves some pretty heavy calculus. It's not necessary for us to go through all of that mathematics. However, if you then graph out the energy as a function of time, basically what you end up with here is just an exponentially decaying energy. That is like so. Now at times t is equal to 0, e to the 0th power is 1, and then therefore the energy that you start with is right here, 1/2 Ka squared. But then as time goes on, that energy undergoes an exponential decay because the amplitude is undergoing an exponential decay. So that's basically what it boils down to, even though of course in this class I'm skipping all of the necessary calculus. Essentially for a damped harmonic oscillator, you end up with an exponentially decaying amplitude as the energy is lost as heat. And then therefore, if you describe the energy lost as heat, you once again end up with an exponential decay. That's basically what it boils down to. Okay, we'll take a look at an example or two in the next video.